my name is Swetha. I built a LIDAR scanner to scan this statue of Kermit and Jim Henson at the University of Maryland. LIDAR stands for Light Detection and Ranging. It's a form of active remote sensing that provides range information by sending out laser light and analyzing what comes back. It's how Waymo's cars autonomously navigate, how high-resolution terrain mapping is done, and how I made this turtlebot navigate this maze. Here's a more detailed system diagram. Starting in the center, our system is controlled by remotely accessing a Raspberry Pi. Our radiation source, a line laser, propagates through the air to the target. The light reflects off the target to the receiver, a Raspberry Pi camera. The data is then stored on the Pi, and once all the photos are taken, with some filtering and trigonometry, XYZ coordinate data is pulled from these photos using Python and OpenCV and then visualized in Cloud Compare. The sensor base is 3D printed. The Raspberry Pi camera is mounted exactly 12 inches from the line laser. Near the laser are slots and a hole to attach the setup to a tripod during scanning. To calibrate the system, I positioned the laser and camera perpendicularly to the wall. I took an image every 6 inches, starting at 18 inches from the wall all the way to 120. We turned off the lights when the photo was taken so the laser appeared clearly. Here are what the images look like. The number indicates the distance to the wall in inches. Notice that as we get further from the wall, the laser line approaches the center line of the image. Then I tuned the radian offset to account for any alignment errors, and adjusted the radians per pixel gain until the curve agreed with my data. Here's a way to visualize this from the top down. Now, given any image taken with the system, the horizontal pixel location of the laser gives us a depth measurement. Here's a look at the statue in the daytime, but to avoid noise, we'll be doing our scanning at night. Here's the system all hooked up and installed on a tripod that lets me adjust the angle of the system. I did a sweep up the statue, so I would adjust the angle, measure it with a measuring app on my phone, and input it to the data collection Python script that saves images the same way it did for the calibration. Despite it being nighttime, you'll notice that the statue is still really well lit because of some construction lights. So to mitigate the source of noise, my wonderful friend held up a blanket each time we did a scan to put the statue into shadow and make the laser show up more clearly. This bright window was another source of noise, but when processing the data, the entire right side of the image is ignored because the distances we calibrated for will never cross into that side of the image, so this window didn't end up being a problem. To be clear, our goal is to make sure that the HSV value of the laser line is very different from anything else in the photo, so that when we apply a filter, we're left with only the laser line. Here's a time-lapse of us scanning the front of the statue. We did about 25 scans in this sweep, so from the top down, this is the area we covered. In total, I did 5 scans, one for each side of the statue, and then one very close to Kermit to capture his smaller details. Here's us scanning the left side of the statue. Luckily, the tripod was sitting on solid, even ground here, but when we did the back and right side of the statue, the ground was freshly laid soil that was not compacted at all. This meant it was really easy to knock the tripod around, which sometimes left a noticeable artifact in the point cloud that I manually removed. Here's what the scans from behind the statue look like. As we traverse up the statue, the number indicates the degrees from horizontal, and the blue line is the laser itself. Here we can really see how the laser profile is reflecting the contours of the statue. Where the laser is close to the center line, the object is far from the scanner, and where the laser is far from the center line, the object is close to the scanner. For each of the 5 scan locations, I used a script called Color Picker to find an upper and lower set of HSB bounds to filter out everything but the laser line itself. Obviously, this isn't perfect, but the rest is taken care of in the data generation script, which produces XYZ values. For each location, I set the HSV bounds, and the script applies the filter to the image. Then the script loops through each row of the image, finds the average pixel location of the laser, calculates an XYZ coordinate, and writes it to a .txt file. It does this for each image in the folder. I opened each location's point cloud in Cloud Compare and manually removed any points I thought were noise. I later implemented a filter in the data generation script to remove any points that were very far from the rest of the points because they were probably noise. As mentioned before, the script also ignores the entire right side of the image. After cleaning up each scan, it was time to combine them into one large point cloud. I used Cloud Compare to translate and rotate each scan until they aligned. This was the most ambiguous part of the project and would be easier with a denser set of point clouds. This white cloud is the front scan, and this green one is the up-close Kermit scan. Here we can see Henson's legs sticking out in the front of the bench, and we can also see the details of Kermit, like his arm, his body, and his face. This orange scan is the back of Jim Henson and part of the bench. These 3 scans were the easiest to align. This pink scan is from the left of the statue, which captured the side of the bench and some of the complex geometry of Jim's face, as well as his arm reaching out to Kermit. And last, in blue, we have the back of the bench, which also captures the back of Jim Henson. Finally, I combined all of the scans into one large point cloud. I was pretty happy with how well you could make out most of the statue's main features in the point cloud, so the next step was to generate a mesh. I did this in Cloud Compare by generating normals and using Poisson Recon. I left the octree depth as the default 8 and made sure that the output density as scalar field was enabled. So the mesh turned out pretty gruesome. I think this was because the points were far apart between each angular scan adjustment. The statue was about 3.5 feet tall and 5 feet wide, so it was a lot of area to cover with the tripod that was difficult to adjust precisely for small angular changes between scans. In the future, I'd like to use a stepper motor with the Pi to make an auto scanner setup, so the setup can complete a very high resolution scan on its own. Without an automatic scanning setup, it would have been wiser for me to choose a smaller scanning target to be able to achieve a higher point cloud density with the same amount of scans to produce a better mesh. Here I'm adjusting the bounds to hide the areas of the mesh with the lowest point densities. The lowest density areas are in blue and the highest density areas are in red. Including low-density areas seem to increase the chance of noisy points creating a sort of phantom surface. I decreased the octree depth to 4, and the mesh, as expected, left out a lot of detail. I also tried increasing the depth to 16, and the mesh wasn't much different than what it looked like for 8, which makes sense because there aren't many points in total. This was a really fun project. Although the mesh wasn't perfect in the end, I learned a lot while working with Python, OpenCV, Cloud Compare, point clouds, and mesh generation, and I'm looking forward to learning more about LiDAR and other remote sensing techniques, and improving the fidelity of the scans with an automated scanning setup.